The 1 in 60 rule has applications other than single pilot navigation. It can be used to determine required heights and rates of descent on a glide slope, calculate distance off required track using radio aids, and for calculating the range of a VOR from the rate of change of bearing. Let's start by considering height for a given range on a glide slope. Firstly, we need a diagram in side elevation rather than plan view. We are coming down the glide slope, we have a height above touchdown, and we have a ground range to the touchdown. Ranges are given in nautical miles, whereas height is given in feet. If we approximate a nautical mile to 6,000 feet instead of 6,080, this carries out the conversion for us and fits in neatly with the 1 in 60 rule. The conversion is within about 1%, which is close enough for 1 in 60 applications. Angle Z represents the angle of the required glide slope. Using the 1 in 60 rule, if Z is 1 degree, when the range is 60 feet, the height is 1 foot. Multiplying through by 10, 600 feet range will give 10 feet of height. Multiplying again, at 1 mile range on a 1 degree slope, the height should be 100 feet. From now on, we will use the term mile to mean nautical mile for brevity. Statute miles are rarely used in aviation. Most glide slopes are set at 3 degrees, or some angle close to it. So, if 1 degree gives 100 feet at 1 mile, 3 degrees will give 300 feet at the same range. We have now come up with the first of our basic rules. A 3-degree glide slope is 300 feet per nautical mile. A 4-degree glide slope is 400 feet per mile, and so on. The required rate of descent is 100 feet per degree per nautical mile. Now try some practical examples. What should your height be on a 3-degree glide slope at 4 miles from touchdown? 1,200 feet. Now another. What should your height be on a 5.5-degree glide slope at 3 miles from touchdown? 1,650 feet. Now let's calculate the required rate of descent on a 3-degree glide slope for a given ground speed. If we were in a PA-28 or a Cessna 150 or similar, our airspeed on the approach would be about 70 knots. Assume a slight headwind. After all, that's why you select one particular runway over another. And a typical light aircraft ground speed is 60 knots on the approach. 60 knots is 1 mile a minute. So when we are 1 mile from touchdown, we are 1 minute from touchdown. On a 3-degree glide slope, what height do we need to be when we're 1 mile from touchdown? "300 feet. So, we have 1 minute to touchdown and we're at 300 feet. We need a rate of descent of 300 feet per minute. Now assume that we've graduated from training and we're in a regional jet. The approach airspeed is 130 knots, and again we've got 10 knots down the runway. Our approach ground speed is now 120 knots. What range will we be at 1 minute to touchdown? "2 miles. So with a 3-degree glide slope, what height do we need to be? 600 feet. Therefore, with 1 minute to go to touchdown, we need a rate of descent of 600 feet per minute. At 60 knots ground speed, the required rate of descent was 300 feet per minute. At 120 knots, the required rate of descent is 600 feet per minute. This gives us our second basic rule. For a 3-degree glide slope, the required rate of descent in feet per minute is 5 times the ground speed in knots. What if the glide slope angle is not 3 degrees? How will this affect the required rate of descent? The easiest way of dealing with this is to work it out for 3 degrees and then factor it for the required glide slope angle. For example, what rate of descent do you need to maintain a 4-degree glide slope at a ground speed of 100 knots? For a 3-degree glide slope, it would be 5 times 100, 500 feet per minute. So, for a 4-degree glide slope, it will be 500 times 4 over 3, which is 667 feet per minute. Call it 670 for practical purposes. Sometimes you need to calculate the change of rate of descent associated with a change of speed on the glide slope. The rule is simple enough. If you decrease ground speed, decrease the rate of descent. If you increase ground speed, increase the rate of descent. However, it can be confusing if the change is given in terms of headwind. An increase in headwind is a decrease in ground speed. So if the headwind increases, you need to decrease the rate of descent. The rule is, for 3-degree glide slopes only, that the required change of rate of descent in feet per minute is 5 times the change of ground speed in knots. So, if we are on an ILS approach into London Heathrow, which has a 3-degree glide slope, and the speed drops from 140 to 120 knots, what change in the rate of descent must be made in order to maintain the glide slope? The ground speed has reduced by 20 knots, so the rate of descent must be reduced by 5 times 20, which is 100 feet per minute. Now, one for you. You are approaching London City Airport, which has a 5.5-degree glide slope, and the headwind increases by 10 knots. What adjustment do you need to make to your rate of descent? If the headwind increases by 10 knots, the ground speed has reduced by 10 knots. 5 times 10 would be a 50 feet per minute reduction for a 3-degree glide slope. However, we have a 5.5-degree glide slope, so we have to multiply by 5.5 and divide by 3. This gives a required rate of descent reduction of about 90 feet per minute. The 1 in 60 rule can also be used in VOR DME navigation solutions. VOR stands for Very High Frequency Omnidirectional Range, and is a radio navigation aid which gives a pilot his magnetic bearing to or from a ground beacon. DME stands for Distance Measuring Equipment, and it gives a pilot his range in nautical miles from a ground beacon. VORs and DMEs are often co-located and share a common frequency and identification signal. Take this case. You are flying along an airway to a VOR DME. The airway centerline is 271 magnetic. Your radio magnetic indicator tells you that your bearing to the VOR is 266, and your DME range is 48 miles. How far are you off the centerline, and to which side? The airway centerline is 271. Your bearing to the VOR is 266. This means that you need to take up a track to the left. Therefore, you are to the right of the centerline. 266 is 5 degrees difference from 271. So if we were at 60 miles, we would be 5 miles right. But we are at 48 miles. 48 is 4/5 of 60. With only 4/5 the distance to go, we are only 4/5 the distance off. We are 4 miles right of the centerline. This could be important. Most airways are 10 miles wide, extending 5 miles each side of the centerline. At 4 miles, you are still inside the airway. When tracking VORs, it is your responsibility to stay within the airway, and you will use these types of calculation in your IFR training. It is also possible to use the 1 in 60 rule to find the range from a VOR when no DME information is available. This can be used only when the aircraft is running a beam or approximately a beam to the VOR. Suppose that an aircraft is tracking 090 magnetic at 180 knots ground speed, and the bearing to the VOR is 002. 5 minutes later, it has changed to 357. What was the range of the aircraft from the VOR at the closest point of approach? The closest point of approach occurs as the VOR is perpendicular to track, in this case on a relative bearing of 270, or when the aircraft is due south of the VOR. You can treat this as 2 separate right-angled triangles of 2 degrees and 3 degrees at the top, but it is easier to treat it as a near right-angled triangle with 5 degrees at the top. The aircraft has a ground speed of 180 knots. This is 3 miles a minute. 5 minutes of flight therefore gives a ground distance of 15 miles between the first bearing and the second. Therefore, we have a situation where an angle of 5 degrees is subtended by a distance of 15 miles. For each 60 miles of range, 5 degrees is subtended by 5 miles. At 60 miles range, the base of the triangle will be 5 miles. At 120 miles, it will be 10 miles. And at 180 miles, it will be 15 miles. Therefore, the range at the closest point of approach was 180 miles. We have seen that the 1 in 60 rule has many applications, other than simple navigation, and that these included glide slope and VOR calculations. You will also find other applications later. For instance, in radio navigation, it can be used in conjunction with the elevation angle of an airborne weather radar, and the range of a weather return to find the height at the top of the weather. The 1 in 60 rule is much loved by examiners, and in JAA questions is often used in preference to accurate trigonometry.